All right, welcome back. So in this video, we're going to be looking at partial fraction decomposition, but from the perspective of the integration rather than the algebra. So we start with a polynomial over polynomial where the numerator degree is less than the denominator degree, essentially a denominator heavy ratio of polynomials. And we are assuming that we have already gone through the algebra of producing a decomposition of each of these ratios of polynomials. So like in the first case, we've got these two factors, x minus 2 and 2x plus 1 downstairs. And so assume we've got the decomposition already. We solve for the a and the b, the a, b, c, and d in this case, and the a here, and then the bx plus c in that case. So we've got the decomposition already done algebraically, and now we want to integrate. And as it turns out, when you go through the integration, there are sort of four forms that pop up whenever you go through the integration in effectively all cases. And so what we're going to do is walk through the integration of each of the forms of these bite-sized pieces. And because if we know how to deal with each of the four forms, then we know how to deal with the integration. So one of these forms is where you have one of these irreducible degree 2 factors with just a number upstairs. Like down here, we've got 1 over x squared plus 4. That essentially takes the form of 1 over x squared plus a squared. If you didn't have a 1 upstairs and this was a 2 or something, the 2 would just factor out of the integral. So having a 1 upstairs is sort of not egregious to think about. And what I like looking at whenever I look at this is like, man, this is almost inverse trig, because if this a squared was just a 1, we'd have inverse trig. So what we're going to do is we're going to factor out an a squared from the denominator, making that a squared a 1. But then if you factor out the a squared from the denominator, you're also going to have to factor out an a squared from the x squared. So then you'll get x squared plus a squared. And now, in order for this to work out nicely, we're going to need a u substitution. So we'll let u equal x over a. Letting u equal x over a, let's see, du is 1 over a dx. Or in other words, dx is just a times du, a times du. So, right, letting dx be a times du and using this substitution, we'll still have the 1 over a squared on the outside, but inside we'll have 1 over, well, x squared over a squared is just u squared, and here's where the u substitution is coming into play very nicely. The dx is just a times du. If we wanted to factor out the a, we'd get a over a squared. I suppose that's 1 over a. Then the integral would just be 1 over u squared plus 1 du, which put this all together, we'd have what, 1 over a times tan inverse of u plus c. So piecing that all together and replacing the u, well, replacing the u, what was 1 over a tan inverse u plus c becomes 1 over a tan inverse of x over a plus c, because our u was just x over a. I put the plus c in a different color here because frankly, sort of as you're working this out, the plus c is sort of less important, I suppose, than the expression of the antiderivative. So we wrote it as plus c, but yeah, we'll have a plus c technically on each of these. Gosh, as I'm smudging this marker around. Now, what's the second form that can occur? The second form is going to be, what if you had an x upstairs with your x squared plus a squared downstairs? This is like this factor down here. If you didn't have an x, but you had like a 5x, you could factor that 5 out. So having an x, just an x upstairs is perfectly fine, well and good. And how are we going to work with this? Well, this is actually u sub friendly straight from the go here. So letting u equal that x squared plus a squared expression here, a is just a number, right? Like the 4 that we would have down here, x squared plus 4 or something. Then the derivative here, the du is just 2x dx. Solving for dx, we'd have dx equals du over 2x. And then substituting in accordingly, let's see, we'd have the u downstairs. We'd still have that x upstairs, but the dx is du over 2x. So let's see, the x's cancel, the 1/2 factors out, and then we just have 1 over u du. But that's just 1/2 ln absolute u plus c. And if we replace u in this case, well, replacing our u, what was 1/2 ln absolute u plus c becomes 1/2 ln. The u was x squared plus a squared, like in this case it would be x squared plus 4. Plus c. So the plus c doesn't even fit, but well, the plus c is sort of less important than the guts of the integral because the plus c just gets tacked on at the end. The third form that we see is when we have just a linear factor, so not a degree 2 factor in this case, but a linear factor to a degree to a higher degree, so like degree 2. So here we've got like 2 over x minus 2 quantity squared, and well, we've got this higher degree term. Now, yes, we got a 2 here instead of a 1, but the 2 could just be factored out of our integral, so having a 1 upstairs sort of tells the story. Well, how are we going to deal with this? Here we'll just let u equal mx plus b. Remember here, m and b are just numbers. This is just a linear factor. And so what du is just m times dx, which means dx is just du divided by m. And then plugging everything in here, we'll have integral of 1 over u squared. But dx is du over m. So factoring out that m, we just have 1 over m integral 1 over u squared du. But 1 over u squared, right, that's just u to the minus 2. And then integrating u to the minus 2, we get minus u to the minus 1. So minus in front, and then u to the minus 1 plus c. And if we replace u and throw u in the denominator, right, so replacing the u to the minus 1 with 1 over u, knowing that u is mx plus b, here we just get minus 1 over m times mx plus b, with one factor of mx plus b downstairs. If we happen to have something like mx plus b cubed, then we just have mx plus b squared downstairs, because what the power rule would increase the power by 1 from a power of minus 3 to a power of minus 2. What about the last case? I should put a star, or at least a couple stars by this, because this is sort of like the case that comes up almost always whenever you're dealing with partial fraction decomposition. What if you just have a degree 1 factor with a number upstairs, like 2 over x minus 2, or 1 over 2x plus 1, or 3 over x minus 2, or 3 over x minus 1? It's very prevalent. How do we deal with this? This will also be u sub, and I don't have a lot of space, but I think I can pull it off. If we have u equal mx plus b, then what du is just m times dx, which means whenever we replace this out, I'll even use some of the space up here. Let's see. The dx is 1 over m du, so I'll factor out the 1 over m, and then we'll just get 1 over u du. And so integrating that, we'd get ln absolute u, so I'll just take the time to write that out as ln absolute u plus c, and well, replacing the u that was inside our ln with what u was, namely mx plus b, we get 1 over m ln absolute mx plus b plus c. And yeah, some of the plus c's don't fit, but so be it. We'll always just throw the plus c in at the end. So now, putting this all together, we can take these 4 forms of integrals that we've computed each case of, and now apply them to the situations where we have already decomposed our rational functions into their partial fraction decomposition. So what we almost want to imagine here is, like, imagine we were not just looking at these functions in their algebraic form, but imagine that we were integrating each of these. Well, because their corresponding partial fraction decomposition is equivalent, we're just integrating the resulting partial fraction decomposition. And the reason that we did the partial fraction decomposition is because integrating the 2 bite-sized pieces here is definitively better than trying to integrate the mess that we started with. And integrating the 4 bite-sized pieces here, so be it. Integrating the 3 bite-sized pieces here, so be it. Each of the pieces comes of these forms, and so we can deal with it bit by bit. So check out this first one here, right? Each of these is just a number over mx plus b. So this last case here, and then, well, what do we get? Well, the 2 sort of would come along for the ride, and then, so you can almost think of that being factored out. The m in this case, the slope is just 1, and so we just have 1 over 1. With the 2 factored out, we just end up with 2 ln absolute x minus 2. What about the second factor? Well, here we've got a 1 upstairs, so that takes exactly the form that we have here. But now the 2 is the slope, so that would give us a factor of 1/2. Don't forget the minus here that's in front, so we'd have minus 1/2 ln absolute 2x plus 1, 2x plus 1 plus c. So there's the result here in the first case. Nothing too wild or crazy, right? I couldn't fit it all in one line, but so be it. Yeah, we're just applying this fact with the mx plus b that we saw previously. What about this second one? Hey, we've got 4 pieces to process here. The first and the last are with the degree 1 factor downstairs, And then the second two are of this form. In fact, one of them has a power 3, but so be it. So how do we deal with the 3 over x minus 2? Well, that integrates to just be 3 ln absolute x minus 2. The 3 factors out, and the x is slope 1, so that's pretty simple. Life is good. What about this second one here? The slope here is also 1, so this factor of m downstairs we don't have to worry about in this case because m would be 1. We do have a minus here, which would intermingle with this minus to make a plus. And so then following the pattern, we just have 1 over x minus 2, because the linear factor is downstairs of degree 1 in that case. What about whenever you had 3 degrees downstairs? Here we'd have 2 degrees after we would integrate, because what is to the power minus 3, when we apply the power rule, would increase to be a power minus 2. The 2 would factor out. The negative here would intermingle with that negative to be plus 2 over, let's see, this would just be x minus 2 squared. And then what about this 1 over x plus 1? Hey, that's just this bottom case. And fortunately, the slope is 1. So 1 over m is just 1. And then we just have plus ln absolute x plus 1. Don't forget the c. And there we go there. So again, I sort of couldn't fit it all in one line. I had to go down, but so be it, whatever. Sometimes these partial fraction decompositions are long, and hence their antiderivatives are long. What about this last one here? We got 3 over x plus 1. Hey, that's straightforward. That's just like this one down here in the bottom. And in fact, the slope is 1. So that's not too bad here. We just have 3 ln absolute x plus 1. When the slope is 1, you don't even have to worry about that 1 over m factor, which is quite nice. What about the next one here? We got minus x over x squared plus 4. Well, hey, that's now of type B here. The x squared plus 4 is like the x squared plus a squared. So we're going to have a factor of 1/2 coming in here. So we have minus 1/2, and then ln absolute x squared plus 4. And if you take a look at that minus 1/2 ln absolute x squared plus 4 and look at it in comparison to this negative x over x squared plus 4, it kind of feels right because the derivative of the u downstairs was 2x. That's why that factor of 1/2 shows up. What about the last one? Now we're dealing with the inverse tangent case. So here, the a that we're dealing with is 2, right? Because x squared plus a squared is x squared plus 4, so the a is 2. So 1 over a is 1/2, similar to the factor that we had in the previous case, but I suppose for different reasons in this case. And then we have tan inverse of x over a, which is x over 2. Throw in the plus c, and that rounds that whole thing out. So there is an evaluation in the latter case where we had sort of the forms from the top of the tree here. Really, as this plays out, the forms at the bottom of this tree are more popular than the ones at the top, but nonetheless, if you can know the forms of the integrals for each of the bite-sized pieces, as we have over here on the right, then you have all of what you need to compute the integrals of the resulting expressions from your partial fraction decompositions. So you do the algebra to get the bite-sized pieces, and then you apply one of these 4 forms to each of the bite-sized pieces along the way. And actually partial fraction decomposition, it's a lot to keep in mind, but it is rather reliable in the sense that you're sort of always getting one of these 4 forms and always processing through this mechanism after having done the algebra of the decomposition. So it's partial fraction decomposition is a lot, but it's reliable, and the more familiarity you get with these things, the more that it will just become sort of second nature, and hopefully that can be that.